There are two other phase changes that we need to mention. These are less common in the atmosphere than condensation or evaporation, but nevertheless are important. When water goes straight from the solid to vapour state, we call it sublimation. Strictly speaking, when water goes from vapour to the solid state directly, it is called deposition, but in meteorology, this change is also called sublimation. Note that both of these phase changes miss out the liquid phase. Sublimation from ice to water vapour absorbs latent heat, and sublimation or deposition from water vapour to ice releases latent heat. In meteorology, it is vital to know how much moisture the air contains at any one point. We can do this using a hygrometer, also known as a psychrometer. Here we see a diagram of one type which uses a wet bulb and a dry bulb arrangement. If air is unsaturated, water will evaporate into it from the muslin, and latent heat will lower the temperature of the wet bulb. If the air is saturated, no water will evaporate and the two thermometers will read the same. The wet bulb temperature is defined as the lowest temperature air will fall to by evaporating water into it at constant pressure. The difference between the dry bulb and the wet bulb decides how moist or humid the air is. The closer they are, the more humid the air is, and vice versa. From these two readings, many values can be calculated, including the dew point, vapour pressure, relative humidity, and humidity mixing ratio. We shall now look at this in a bit more detail. The dew point of the air is the temperature to which air must be cooled at constant pressure to reach saturation. Do not confuse this with the wet bulb temperature, they are different things. The dew point of the air will only change if the amount of water vapour in the air changes. Remember when we talked about the difference between dry and wet bulb temperature readings? Well, in a similar manner, the difference between the dry bulb temperature and the dew point signifies the humidity of the air. When the dry bulb temperature equals the dew point, there is 100% humidity or saturation, hence cloud or fog will form. If the dry bulb temperature and the dew point are many degrees apart, the air is relatively dry. In fact, at saturation, the dry bulb, wet bulb, and dew point temperatures are all exactly the same. The dew point lapse rate varies enormously on any one day, with large changes in both spatial and temporal contexts. But on average, the humidity mixing ratio lapse rate is 0.5 degree per 1,000 feet. A simple rule of thumb is that the difference between the dry bulb temperature and the dew point is equal to 100 minus the humidity divided by 5. Here we see two boxes containing moist air. However, one is more moist than the other. In the atmosphere, each constituent gas that makes up the air exerts its own pressure. It is the sum of these pressures that actually makes up the total atmospheric pressure that we often use in aviation. Water vapour is the same. It is a gas. Therefore, it exerts its own pressure, and this we refer to as the vapour pressure. In our diagram, the box on the left has a lower vapour pressure than the one on the right. Therefore, the pressure being exerted on the walls of the container by the water vapour is less. Let us consider an enclosed box, half filled with water, with air filling the rest of the box. Initially, the air above the water is unsaturated. There will be a value for the vapour pressure. However, evaporation will immediately start to take place. If we left this box alone for long enough water will have evaporated from the water surface for the air to become saturated. At this point, evaporation will stop, and the vapour pressure will also cease to rise. This maximum value of the vapour pressure occurs at saturation, and is called, unsurprisingly, the saturation vapour pressure. We are now going to talk about humidity and its measurement. We can reference humidity with two specific terms: relative humidity and absolute humidity. Relative humidity is the percentage degree of saturation, or put another way, it is the amount of water vapour a body of air actually contains, relative to the maximum amount it could hold, expressed as a percentage. A relative humidity of 100% is saturation. Absolute humidity is the mass of water vapour contained in a unit volume of air. It is expressed in terms of grams per metre cubed. Humidity mixing ratio, or HMR, is a similar property to absolute humidity, in that it is a measure of the amount of water vapour contained in a sample of air. But whereas absolute humidity is the mass of water vapour in a unit volume of dry air, the humidity mixing ratio is the ratio of the mass of the water vapour to the mass of the dry air. It is expressed in grams per kilogram. In temperate latitudes, the HMR value lies somewhere between 5 and 50 grams per kilogram. In unsaturated air, the HMR remains constant with increasing height, whereas pressure and temperature decrease. Saturation mixing ratio, or SMR, is simply the HMR when the air is saturated. That is all for the humidity lesson. We have looked in detail at water and its phases or states, and also the practical implications of changes between these phases. As we have seen through this lesson, water plays a major part in the atmosphere and the weather, despite the relatively small quantities in which it exists.